go. All right. So this is the data file that we've been working with, and so we went through this last time. We've got the main difference in this data set is the difference between fresh fat and rancid fat. So you see that these two means are really different. These two means are also different, but they're not nearly as different as these two means are, which is why when we look at the sums of squares due to column, that's where most of the variation is. That's what the sums of squares is. It's quantifying variation. That's where most of the variation is. The next most variation is due to differences in rows, the differences between males and females, and very little of the variation is due to this interaction. And what that looks like when we graph it is that we see the main effect is a difference between fresh fat and rancid fat. There are differences between males and females, but they're not statistically significant because they're swamped out by the big variation between fresh and rancid. Now, what I asked you to do here today at the beginning was to flip these things. So if we basically take what was fresh and put it in the rancid category, and what was rancid and put it in the fresh category, we get an ANOVA table that looks different. It's still the same in many ways because it still has the same amount of variation total. It still has the same variation total, 77,570. Still has the same amount of variation that is in subgroups, but now the subgroup structure is rearranged such that when you look at the column means are not terribly different from one another, which means that the effect of fat type isn't as significant as it was before. And when we look at sum of squares columns, we see that sum of squares column is now the same amount of variation as we had in sum squares for the interaction before. And it's because we took all the variation that was due to column structure and we rearranged it so that now it's not spread across the two columns evenly, it's spread across the two columns unevenly. And so what we've done by rearranging the data is we restructured the ANOVA table such that variation that was accountable to fat type is now found in the interaction term. But you'll see, I'm going to flip this back, these two things have basically just flipped when we flipped these two sections of data. (61,204,083) and 918.75, and now it's 91875 and 61,204.8. So if you run this, if you do hand calculations on this table, you will get that ANOVA table. And so here they are, side by side. This was the situation where fat was the main effect and the only thing significant. This is the sums of squares for fat. This is the sums of squares for the interaction. By flipping fresh and rancid fat in the males, it forces the fat type to be very similar in mean. And also, these row means are exactly what they were before. So the row means haven't changed at all. So as a result, the sums of squares row hasn't changed at all. All that's happened is the sums of squares columns has changed. And so because sums of squares column is now accounting for less variation than it was before, all of that leftover variation is due to this interaction. And what this looks like is instead of males and females both being high under fresh and males and females being low under rancid, by flipping the fresh and rancid data around, artificially flipping it, what we've basically said is that males respond to fresh and rancid fat differently than females respond to fresh and rancid fat. Females grow best with fresh fat, Males grow worse with fresh fat, males grow best with rancid fat, and females grow worse with rancid fat. And so what the interaction term is basically saying is, are the two treatments different from one another depending on what the two treatments are? So in this case, the question is, do males and females respond the same to the two different fat types, or do they respond differently? If males and females respond differently to the two fat types, that interaction term becomes the significant part of the two-way ANOVA. Males behave one way, females behave a different way when exposed to these two treatments. And so anytime you see that these lines are not parallel, and they can be not parallel like they are in this case by crossing, they can also be not parallel by converging or not parallel by diverging. It doesn't really matter. What matters is, are the two lines parallel or not? If they're parallel, there's no interaction. If they're crossing or diverging or converging, you will expect to have a significant interaction. Once again, all that interaction says is that one of your categories, in this case male and female, they behave differently depending on what the other category is. And that's what the interaction term is. So, the last thing that I want to talk to you about is, I mentioned this a long time ago, this idea of fixed versus random effects. I mentioned this at the beginning of the treatment of analysis of variance in a single factor situation. Single factor analysis variance, it doesn't really matter if your variables are fixed or random, because you're always going to be dividing the mean squared treatment divided by the mean squared residual, or mean squared error, or mean squared within, whatever you want to call it. But when you start to have two or more factors, two or more treatments, whether that treatment is a fixed effect or a random effect becomes important, because that affects how you calculate F. So these are all F statistics. Mean squared treatment divided by mean squared residual. Mean squared treatment divided by mean squared interaction. So what we mean when we talk about a fixed effect is a situation where, like male and female, if you want to think about rats in a purely binary sort of way, all rats are either male or female. There's no third option. You haven't randomly selected males and females from a universe of possibilities of sex in rats. You've selected males and you've selected females because that's the two things that you have. And that's what it means to be a fixed effect. Are you randomly sampling from a universe of possibilities, or are you sampling all the possibilities that are possible? Another way of thinking about a fixed effect is, there are a bunch of possibilities out there, but I'm actually just only interested in these two possibilities. So for example, if I'm interested in college students, I could sample college students at William Jewell College, at Avila College, at Rockhurst, at Park. But if my population that I want to extrapolate to is all colleges and universities, this is kind of a non-random sampling of all colleges, because these are just some smaller colleges that I have connections with here in the Kansas City area. But if I'm using those to stand in for all colleges, then this is a random sample of all colleges. Same thing if I added to these KU, MU, K-State. This isn't all colleges, this is just a random sampling of colleges. This would be a random effects model. But if what I really wanted to know about was liberal arts colleges in Kansas City, that now becomes a fixed effect, because I sampled all of these small liberal arts colleges in the Kansas City area. And my question has to do with liberal arts colleges in the Kansas City area. In that case, that would be a fixed effect. And so whether something is a fixed effect or a random effect depends upon what the population is that you're wanting to say something about, and also depends on how you chose to sample that population. If you're sampling all the possibilities, liberal arts colleges in the Kansas City area, then that's a fixed effect. Because all you're trying to do is say something about those colleges. You're not trying to extrapolate those data and say something about what would happen at KU or K-State or MU. If you wanted to talk about large state schools, you might say, large state schools in Kansas and Missouri, then you might say Wichita State and K-State and KU and MU and Missouri State, et cetera, et cetera, et cetera. You would gather up all those, and that would basically be a fixed effect because it's not a random sampling of large state colleges. It's all the large state colleges that you're interested in. If you wanted to say something about large state colleges in Kansas and Missouri, and all you sampled was MU, Missouri State, KU, and K-State, that's now a random effects model because you want to say something about large state schools in Missouri and Kansas, but you've only randomly selected 4 colleges from that pool. So are you using a random selection of possible treatment levels, or are you selecting treatment levels that are specific in some way? That's the difference between fixed and random effects. So the reason that this becomes important is how you calculate the F statistic. So if you have a two-way ANOVA and both of these are fixed, which is actually what we're doing with this particular experiment, we have rats. They're male and female. We have fat. It's either fresh or it's rancid. It's not mostly fresh, a little less fresh than it could be, kind of sort of rancid and really rancid. It's not a continuum. It's these 2 categories, and presumably there are only 2 categories, fresh fat and rancid fat. So both of those would be fixed effects. In that case, you divide your mean squared sex and mean squared fat type by the residual. And you would also do the interaction divided by the residual. If they're both random effects don't get divided by the residual, they get divided by the interaction term. So if they're both random, both of the random effects get divided by the mean squared interaction, not mean squared residual. If A is fixed and B is random, A gets divided by the residual by the interaction. B, because it's random, gets divided by the residual, and then the interaction gets divided by the residual. And there are 2 versions of this. One is unrestricted and one is restricted. I tend to use the restricted version. It's a little more conservative way of finding differences. So all that changes when you do random and fixed effects is how you calculate F. But you need to do it the proper way. So you need to think about, are these things that I'm looking at, are they fixed or are they random? In the gecko example that you are looking at, are those 2 populations, Galveston and Oklahoma City, are those fixed or are those random? Some of you are saying fixed, somebody said random. Why do you think they're fixed? So there are other locations that they could be, but I just chose those 2. That doesn't sound like fixed to me. That sounds like random. They're a random collection of all the possible populations of geckos that I could have chosen. I could have chosen, instead of Edmond, Oklahoma, and Galveston, I could have chosen Nacogdoches, Texas, and Dallas. I could have chosen Brownsville, Texas, and Dallas. I could have chosen Brownsville, Texas, and Pittsburgh, Pennsylvania. So those are a random effect because I chose those 2 populations out of the wide variety of populations that I could have chosen. Summer and winter, fixed effect or random effect? So you might argue that it's random because I could have also chosen spring and fall as well. But in this case, I would think of it as a fixed effect because I'm not really interested in spring and fall because spring and fall have intermediate temperatures out there in nature, and I wanted to select extreme temperatures. So I collected geckos in January when it's really hard to collect geckos, and I collected geckos in the middle of summer when it's really hot, because I'm actually not interested in spring and fall. I'm not interested in intermediate temperatures and how they're affecting these animals. I'm interested in how very cold temperatures affect them and how very hot temperatures affect them. And so in that case, those I would view those as fixed effects because of the questions that I have. Now back to Blaine's deal with fixed effects for the populations. In reality, I would also consider those fixed effects. And the reason why is that I wanted a very southern population and I wanted a very northern population. And so I'm not actually interested in all the populations of geckos out there. I'm interested in far north populations and I'm interested in far south populations. I'm interested in those two extremes. So if I got back my report from you doing a two-way ANOVA on these data rather than one-way ANOVA, and you were treating those populations as random effects, I would probably write back to you and say, no, they're fixed effects because I'm interested in these two particular populations. And they're not standing in as a representative for all possible populations. They were chosen specifically because of their latitude. And then the statistician would have to go back and redo his analysis slightly, his or her analysis slightly. So fixed and random effects can be a little tricky. Can I help you?
No worries.
Okay. So sometimes determining what's fixed and random effects can be a little tricky. And this is why whenever I have you write a report, I have you write a section at the beginning of it that basically says, here's how I, the statistician, understand what your data are about. Because then that gives the researcher an opportunity to say, yeah, that's not what my data are about. My data are about this other thing. And then you clear that up early because you had the forethought to define for the researcher, here's how I'm thinking about your data. You need to let me know if this isn't the way that you're thinking about your data. So that's why that part at the beginning of the report is important, that introduction part. Because you may actually think of something as a random effect for good reasons, and the person that you're analyzing data for may think of that as a fixed effect for also perfectly good reasons. So that's the last thing that you kind of need to know. Before we get started on this, I do want to go and do one other thing though. In your P's analysis, I've gotten some emails from people with some coding questions. And so in the P's analysis markdown document that I sent you, this is the final figure. And you see that I have the treatments on the bottom here. I've got the means and the 95% confidence intervals. And I've also put letters above each of these to show you what things are different or not. If letters are different, that means that those treatments are different. If letters are the same, it means those treatments are the same or not different. And so what I've included in this R document is a somewhat more involved graphing block than you have from your live coding. And the reason that this is more involved is I'm asking this graphing block to do more things. And so we haven't gone over some of these things in class, but look at this graphing block and put it up next to your graphing block from what we've done in live coding, and you'll see some differences. So for example, I'm putting limits on the y-axis. Well, the reason that I'm putting limits on the y-axis is I'm actually using ylim, which puts these limits on the y-axis, so that I have a little more space at the top of my figure so that I can fit that letter in there. Other things that I'm doing is I've added this thing here, which is geom text, and it's referring to a column of the CI plot 2. So I generated CI plot 2 up here that looks like this. It has the means, and then I had to do all that back transformation to get the upper and lower ranges of the confidence interval. But you'll see that it doesn't have any letters in there anywhere. So I had to go and add a column of letters to that data frame so that I now have data that will I now have these letters in that data frame that I can add to that plot. So this is a line of code that is basically telling me, I want you to put some text on my plot. I want you to find it in the CI plot, in the confidence interval plot data that I generated from summary SE. I want it to be size 4. The label that I want you to print is the label that is in the column group. I want you to put it someplace. I want you to put it just above the upper range of the confidence interval. I want you to align it by treatment on the x-axis. I want it to be, actually this sizing is actually redundant. There should only just be one sizing here. So I got rid of that size 6. And I want you to do it in a serif font rather than an Arial font or Calibri or whatever the default font is. So I've added things to this graphing block that are things that we didn't go through in class. Part of your job as being an inquisitive, curious scripter is, oh, Dr. Quincy's final graph looked like this. What did he do differently with his plotting that made it look like this? And figure out what those things are. So that markdown document is on the Moodle site for a reason. So pay attention to that. All right. So let's go to town. Let me get myself a new script. So at this point, you guys have probably already done this. Okay, so we should all be at this point right now, right? Everybody at this point in their R script? Okay, good. So let's load a couple of libraries that we're probably going to need. We're probably going to need RMISC. We're probably going to need ggplots2. We're probably going to need car. Let's just start there. And those should all just load right up for you because you guys have been using these. So what's the first thing we want to do with these data? So the first thing you do is you read in your data and you clean up anything that needs cleaning up. What's the next thing that you want to do in an analysis structure? So you want to check for assumptions. What are the two assumptions? One of them you already said is normality. And the second one is homogeneity of variances. How do we check for normality? So we do a Shapiro-Wilks test. Do we do a Shapiro-Wilks test on the raw data? You do it on the residuals. How do we get residuals? So we'd have to specify a model. Okay, good. So what is this model going to look like? Okay, what kind of an ANOVA will this do for us? This will do a one-way ANOVA, but we actually want to know the effect of sex and fat type, right? So how do we need to alter this? Simply.
Well, you have to add in facts. You have growth and sex. If you have growth, so you have to add in that somehow. OHD plus that.
Okay, try that. So get this model in, and then do summary model 1 to give you the ANOVA table. What is it in my data file? Oop. Oh, but I haven't read in my data yet. No, I have read in my data. Yeah, I did. Okay, all right, fine. Lose my mind. What's this? Who was that? Yeah. When you've got this done, put your green sticky up. Let me see.
Wait, this is, that's what I did.
Aha,
Never
data
mind,
excel.
sorry.
Yeah, there you go. Okay. Wait a minute. Yeah, it hasn't done anything. What is your data file called?
Data.
Don't ever call your data file data because data means something
Oh.
to R. So that's going to just confuse R. Don't confuse R. R is simple-minded. Now get summary model. Woo! Okay. Does everybody get this? Jonathan? Yep. Okay. All right. Green tabs down. What's wrong with this? What's wrong with this ANOVA table? Oh, you did not do it. Okay, Chance. Yeah. What's up? Do 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 do. There's no unexpected parentheses in there. That's weird. Let me see. Let me see your structure thing. That's weird. Try retyping it. It sounds stupid, but just try retyping it. Don't copy and paste.
Yeah,
just retype it. Yep. Okay. Yep.
Same error.
Well, that's just stupid. Okay, hold on. Now it's saying you have a different problem. Expected symbol in model 1. That's a tilde, right? That is a tilde in there, right? Yeah, okay. Wow, weird.
Hello, I can try rebooting it. You can move on and come back. Go ahead. I can
Okay,
try
yeah.
restarting this.
Yeah, I don't know why that's not working. That seems exactly what it should be. Actually, there is something that might be causing a problem. Um, just general advice. There are certain things that R doesn't like. So just incorporate these into your thinking. R doesn't like blank columns and blank rows in the middle of data sets, R doesn't like it doesn't like spaces in column names. So one of the problems you could be having is you could be having a problem in that you have fat type as two words. So first thing I would do is I would change your column name. If you want to keep fat type, I would make it all one word, or as you can see in mine, I just called it fat. I'm surprised that when it imported it in, oftentimes if you have something like this written as a column heading, when R imports it in, it will typically replace that space with a dot. And for some reason, it didn't do that when it imported it, and that's actually probably the problem. So one of the ways you could do is you could redefine that column. So just use dat $fat type as you have it originally written. Assignment operator, yep. And then dat and rename it. Just rename it. Fat, something simple. Okay. Now, oh yeah, yep. Yeah, sorry, I did it the wrong way in my head. Why is it putting quotes around it? Okay, try that. Yeah, that's the issue. Yeah. So try putting it in quotes. Yeah, see if that works. Yeah. Yeah. That's what the issue is. Okay. Well, Chance, so you can go back and just fix it in your original data file, and I'll bet it will work fine for you now. All right. So what's wrong with this ANOVA table? If we're doing a two-way ANOVA, it doesn't have an interaction. So it's giving us the main effect of sex. It gives us the main effect of fat, but it's not giving us the interaction. It's because Blaine told us to put a plus sign in here because he said added to it. Try it with an asterisk, which means multiplication. Same line of code, just change the plus to an asterisk. See if that fixes things. What you should now see is that you have sex, you have fat, you have the sex by fat interaction, and you have the residual term. Put your green sticky up when you get that.
I just did the same thing.
Did you rerun that line?
Yeah. Oh, you're gonna do it again?
Yeah, run it again.
It's not seeing the asterisk. Do I need to?
No, that's irritating as can be.
Maybe
Nope. What is it? Is it Alt? No, Control. What the heck? This may be one of those differences. Yeah, okay, so. Something is definitely wrong because it's also showing you that you have a significant sex effect, which you should not be having a significant sex effect.
Want to reload my branch maybe?
No? We're still in here. weird. I don't know. We're almost out of time, so come by my office. So if you want the interaction, what you have to do is you have to put this as a multiplicative factor. And what it will do when you do that is it will do the individual effects, and then it will also add in that interaction term. The other thing that I want you to see is when you compare these two ANOVAs, the two ANOVA tables, you see that when you didn't give it the interaction term, it took whatever variation was in the interaction term that wasn't included here, and it just dumped it into the residual. Residual is just unexplained variation. And so if you don't tell it that there's an interaction term, it takes whatever variation is accounted for by that interaction term and throws it into the residual category. And the problem with that is that as that residual category gets bigger, remember that in an ANOVA, what you're testing is you're testing the F ratio, which is the mean squared effect, whatever the effect is, whether it's fat or sex or whatever, is divided by mean square residual. And so any variation that is unaccounted for gets thrown into the residual. As this thing gets big, this whole thing gets small, and as a result, it's difficult to see differences. You end up with non-significant F statistics. And so by accounting for the interaction, you take variation out of the residual category, you put it into the interaction category, it makes your residual value smaller, which then makes it easier to see effects if they exist. And so when you look at this 11,667, if you take 12,585, subtract 919 from it, you should get 11,667, because it just basically took all of this variation that was due to sex by fat and threw it into the residual category. This is the first step of running this. You still need to check assumptions. So homework for Monday, generate residuals from this model, test it with a Shapiro-Wilk test, and then also check homogeneity of variances. How do we do that? We do that with a Levine's test. Chance, did you get yours to work finally?
Yes.
Okay, good. So we'll fix you. Blaine, we need to fix you. Levine's test for homogeneity of variances. So run those and have them ready to talk about on Monday. I will see you back in here on Monday as we continue to work our way through this. What went well, what didn't go well on the stickies. And I will see you guys on Monday. The reports due, yep. If you have questions on the report, let me know. Yeah.
I think that question